Assalamualaikum warahmatullahi wabarakatuh and a very good day. So I hope you all are in a good condition and can pay attention on this topic. So this is actually the subtopic under topic 2, which is the transformer. So this is the list of the subtopic that we will learn in this topic. And the transformer, so this is the figure showing a different type of transformer that use in the practical environment. So this is transformer used in the power transmission, distributions, and so on. And this is a transformer used in our home appliance, electrical home appliance. And also several figures. So actually the word transformer means that it is an electromagnetic device which transform electrical power from one end to another at different voltage and different current, but keeping the frequency constant. Okay, so unlike motor or generator, it is a transformer is a static machine. We have a different turn ratio on the primary and the secondary side that which can actually change the voltage and the current. And the voltage and current that can transfer into can be changed into a transformer must be AC voltage and current. So DC voltage and DC current cannot use transformer. And the rating in the transformer is either in kVA or MVA, okay, kilo VA or MVA. This is actually apparent power because the load connected is unknown. And the transformer are adapted, so the construction and so on is actually depends on the numerous engineering applications, depend on the power level used, the frequency, application, cooling time, and so on. And this is the example of transformer classifications. So we have what called a three-phase transformer. We can have also distribution transformer, instrument transformer, for example, the voltage transformer, current transformer used for the measurement and so on. And for isolation transformer, this is used for isolation. So actually the transformer, the invention of transformer can actually has a very good impact on the power system, where actually by using this transformer we can actually transmit the power, the high voltage, sorry, the high power in a very long distance. Okay, because usually when we want to transmit power in a long distance, we have a lot of losses. Okay, so by using transformer, what we do from the generator to transmit, we need to step up the voltage. So when you step up the voltage, okay, the current will actually become lower. So we transmit this power by having a high voltage but low current to actually limit the losses, because losses is usually associated with the current. Higher current meaning that higher losses. Okay, so we transmit in a high voltage so that we can actually minimize the losses. So this is actually the block diagram that shows the power transmission system. So we have the power plant always usually in a very remote area, and then we need to transmit this power generated. Okay, so what we do is actually we step up the voltage by using a step up transformer and then transmit, and then in a long distance here, and then we are using a step down transformer again to step down the voltage to the required voltage demand. For example, the industry requires maybe 11 kV, for the commercial maybe 415 volt, and for our home is 240 volt. So this actually slide actually showing the previous figure, and this is also where the transformer is used in the power transmission. Okay, so generation, you step up and then transmit, and then we step down again for the distribution level. And the transformer in its basic form is actually a device, electromagnetic device that has two windings, what we call the primary side, and the second winding, which is we call secondary side. Okay, and between the primary and secondary, there is no electrical connection. Okay, both coils are actually connected through the flux linkage. So this is actually the basic structure of the transformer. So we have the winding here and also the secondary here. We have the winding. N1 is the number of turn of the primary, and N2 is the number of turn at the secondary. So actually this one shows actually what it's all about. So when a voltage Vp is applied to the primary winding, so we have a current that will flow here. Okay, so when we have current, so a flux, okay, will actually induce, okay, inside this core, and this flux will link to the secondary. And since we have flux here, so based on the Faraday's law, when you have flux, okay, the flux is actually positive and negative because we have AC supply. So we have what I call some change of the flux direction here. So it will produce what we call the EMF, which is based on the Faraday's law. And the construction, so the core is actually can be either in the square or circular, depends. So for the square is for small capacity of transformer, and for the circular is for three-phase or higher rating transformer. So as you can see here, the core is not a solid core, it's actually a laminated core. Okay, we have a species of iron core here, we have the pieces of core here that is laminated, okay, and then arranged to be what we call a single core here. So this is actually laminated, is used to reduce the eddy current. And the laminated type, the construction of the core can be either in the core, UI type, or the shell type, where for the core is actually either in the step of U and I shape laminations, and the primary and the secondary winding are wound on two different legs of the core. While for the shell type, it is constructed from a step of E and I shape laminations, and the primary and secondary winding are wound on the same leg of the core, like these figures. So as you can see here, we have what called core type, and then this is a shell type. And for the core type, we have both winding. It's actually wound up in the different core here, in a different leg, different branch. While for the shell type, both winding are wound in the single branch. So this is the shell type, which is the either EI lamination or EE lamination, and core type, which is LL or UI lamination. And usually the primary winding is actually in the side, and the secondary winding is actually at the outer side. And this is the figures showing the EI lamination type for the core, and this is the actual figures of the what I call the shell type. Okay, the shell type where we have E and I lamination structure here for the core. So the ideal transformer. So for the ideal transformer, we assume no losses. So we have a winding resistance 0 and no leakage inductance. And this shows the ideal transformer. So current, a small current, what we call the magnetization current, IM, is required to generate a flux. Okay, when you have the flux here, so we will actually induce, which is E1 right now. This is E1, is different from V1. V1 is the supply, E1 is the voltage induced at the primary side. And then when we have the current flow here, it will magnetize this core, and the flux will actually flow inside this core and link with a secondary winding here. So when we have a flow of the flux, positive, negative, okay, back and forth, so will induce a voltage here, E2 here, okay. And this is the So this is unloaded transformer. So since this is unloaded, no load is connected to the load terminal here. So as you can see, the current secondary is 0. Okay, and this is the voltage induced at the primary side and the voltage induced at the secondary side. As you can see, the value of the flux is the same. The only difference that actually determine the value of the voltage induced is the number of turns. So this is the ideal transformer. When you loaded the transformer with a load here, so since we have a current, so when we have a voltage here, and then so meaning that you have a current flow, okay, I2 flow here. So this I2 will actually induce a flux, which is we call I2 here. Okay, sorry, flux 2. So this flux will actually link again with the first primary. So the first primary, so when we have flux, so we have also the voltage which is already induced, and it will also have what we call induce what we call I1. So for the loaded, so we have seen that there is no I1 and I2, but when you connect the load, so we have what we call I2 and also I1 induced at the primary side. And this is the relationship between the number of turns, the voltage induced, and the current. And A is normally used to represent N1 over N2. And I would like to mention that the power input is equal to the power output, meaning that the power at the primary side is equal to the power at the secondary side. So this is for the ideal transformer, okay? And so when you have A is equal to 1, so meaning that this is ratio 1 to 1. So this is usually transformer for isolation application only. And then for A, when you have A is lower than 1, so meaning that your N2 is larger than your primary side. So this is a step up transformer. And when you have A is larger than 1, so this one is actually a step down transformer. So the transformer rating is usually based on either voltage ratio and power rating. So usually for small transformer, we are using watts, and for the larger transformer, we are rated, the transformer are rated in apparent power. So example 1, so determine the turn ratio of this transformer. So very easy. So the A is just the division between B1 and B2, so which is 20. So meaning that this is a step down transformer. Okay, and example 2, step up either transformer deliver 50 kilowatt to resistive load. So calculate the turn ratio. So the turn ratio is very easy. So A, which is N1 over N2, which is you can calculate, which is 0.2. And this is the interesting part, the primary current. So the primary current, so the voltage at the primary is 480, and the power given is 50 kilowatts. And we know that relationship between power is actually VI cos theta. But right now, the cos theta is actually 1 because resistive load, meaning that the current and voltage are in phase. So 50 kilowatt over the voltage, which is 480 volt, so you can get the primary current, which is 104.17 ampere. And for the secondary current, you all can always use the equations of I1 over I2, which is equal to N1 over N2, which is this one is 0.2. So meaning that I2 is 0.2 multiply 104.17, which is you can get around 20.83 ampere. And this is exercise 1. So I think this one we will actually discuss, or maybe I will do the solution and then I will distribute to all of you. Okay, but you have the answer, so you can try first. And this is the nameplate of the transformer. So usually this nameplate are for higher capacity transformer, a big transformer. So when you have a big transformer, you will have this nameplate that shows all the rating and so on, the information about the transformer. And so this is the ideal transformer. Lastly, the model that we use. So this is the voltage supply and the voltage load. E1, the voltage induced at the primary side, and E2, the voltage induced as the secondary side, I1 and I2, and the number of the ratio. And you can always use this equation to have to solve any problem that related to the this transformer. So since this is an ideal case, so for this one is we can always assume that V1 is equal to E1 and E2 is equal to V2, okay? Because there is no other element here. And for simplification of the calculation, so we can always refer the secondary side to the primary side. Okay, so when we do here, we can actually can have our primary side impedance is equal to A square Z load, and we can actually redraw again like this. And we can also actually transfer the primary to the secondary. So when we transfer the primary into the secondary, so we can have this circuit. So the practical transformer. So this is the practical transformer. So meaning that we need to consider losses, leakage current, and so on. Okay, so in this syllabus, we concentrate or we actually consider the winding resistance, the flux leakage, and then the finite permeability of the core and the core losses. So in the practical, so magnetic core, which is is actually got a finite permeability, okay, and magnetizing current is always usually required to establish the core. Okay, so this effect can be represented by magnetizing inductance, which is Lm, and the core loss can be represented by the Rc here. Okay, and as you can see right now, we have the IO, which is IO is actually IC plus IM, and so we can actually modify the equations, the relationship equation. So right now, I2 is not over I1 any longer because we have another one here. So I2 is equal to I1 prime. Okay, and your I1. So and then based on the KCL, we can obtain relationship between I1 is equal to IO plus I1 prime. So this is when, okay, and then next is actually on the winding resistance and the leakage flux. So finally, so R1 and X1. So this one, R1 represent the internal resistance of the primary winding. X1 is the leakage inductance at the primary side. And we have R2, which is represent the internal resistance of the secondary winding, and X2 represent the leakage inductance and at the secondary part. So we have what we call these parameters R1, X1, R2, X2, and RC, and also XM. Okay, this is the complete equivalent circuit. So this is a phasor diagram and approximate equivalent circuit. So why we need to approximate? Because to make our calculation easier without sacrificing the accuracy of the model. Okay, so actually, as you can see, based on the previous study, okay, so R1 and X1 can be transferred into this part, okay. this one can be done, okay, to our calculations, and this can be done without any calculation error. So okay, so we can actually write or redraw the approximate equivalent circuit of the transformer like this. And we can also represent the secondary to the primary side. Okay, so we have R2 prime, X2 prime, I1 prime, and also V2 prime. So what is this? So V2 prime is actually when referred, this is actually a V2 that transfer into the primary, which is 2A V2, and I1 prime is I2 over A, while R2 prime is A square R2, and X2 prime is actually A square X2. And we always can actually remove this what we call the isolation here. So we can also draw the approximate equivalent circuit of the transformer like this. And we know that R1, R2 can be combined together with X1 and X2. So we can have R equivalent 1 and X equivalent 1. Okay. So a 100 kilo VA transformer has 400 turn ratio and primary. So this one A is equal to 400 over 80. So your A is 5. Okay. And your primary and secondary resistance, okay, is actually this one, 0.3 and 0.01. So you can always use R equivalent 1 is equal to R1 plus A square R2, which is 0.3 plus 25 multiplied with 0.01. So you should get this one is around 0.25 plus 3 is 0.55 ohm. Okay, and X equivalent 1 is X1 plus A square X2. So this one is 1.1 plus 25 multiplied 0.03. So this one is actually equivalent to 1.975. And your Z equivalent 1 is 0.55 plus J 1.975, which is, by using calculator, is polar, so you should have 2.05 ohm. Okay, so your answer is 2.05 ohm, and for the equivalent when transferred to the secondary is I think I need to do this one. Okay, so you can always use the formula of Z equivalent referring to the secondary is Z equivalent 1 over A square. Okay, so this one is 2.05 over 25. You should get the answer 0.082 ohm. So the transformer test, we will go on the next video. Thank you very much.